here, 10 million light years from planet Earth, every point of light is a galaxy containing billions of stars. And yet, we've managed to map the visible universe well enough to chart an accurate course all the way back home. Just within the last 100 years, we humans, inhabitants of a small planet orbiting this unexceptional star, have learned where the galaxies are, what they're made of, and how they got to be that way. We've discovered that the universe was born in fire 13.8 billion years ago. And that it's been expanding and evolving ever since. But with new instruments on Earth and in space, we've begun to glimpse how much we still don't know about the cosmos. This is Neil deGrasse Tyson, and I'm here to guide you through a century of discovery about the past, present, and future of our universe. Our story begins in the 1920s, when astronomers, using what was then the world's largest telescope on Mount Wilson, near Los Angeles, began piecing together our place in the cosmos. The astronomers knew that we live in a disc-shaped galaxy called the Milky Way, and that the band of light arching across the sky is our view of that galaxy from our location inside it. But their observations hadn't yet revealed whether any other galaxies existed. That changed when the astronomers aimed their telescope at a fuzzy patch of light in the constellation Andromeda. Identified pulsating stars like those in our galaxy. By measuring the stars' distances, they found a galaxy in its own right, far outside the Milky Way. The Andromeda Galaxy is more than 2 million light years from us. So we see it as it looked more than 2 million years ago, long before humans first walked the Earth. As they probed deeper and located many more galaxies, the astronomers were startled to see that the light from distant galaxies was always stretched out to longer, redder wavelengths, signifying that they were all moving away from us. They found that the more distant a galaxy, the faster it's moving. Cosmic space is constantly stretching, carrying the galaxies with it. But there's no center to the universe. An observer in this galaxy would see the same evidence of cosmic expansion as we do. So so would observers in that one there. Wherever you are, it looks as if you're at the center and everyone else is speeding away. As the universe expands, it cools, its energy thinning out across a growing volume of space. The overall temperature of the cosmos today is only 3 degrees above the coldest possible temperature, absolute zero. But if we ran time backward, all that energy would be compressed into a shrinking volume of space, and the universe would get hotter. Realizing this, a few scientists calculated that the entire universe must have once been hotter than the sun. Skeptics ridiculed the idea, naming it the Big Bang Theory. But then, in 1964, 2 astronomers at Bell Labs in New Jersey started testing a horn-shaped radio antenna. They wanted to detect the natural radio waves produced by gas clouds in space. Instead, they encountered something they couldn't explain. Low-level energy coming evenly from all directions in the sky. Without realizing it, they had made one of the most profound discoveries in human history. Light from the Big Bang itself, released when the universe was only 380,000 years old, less than 1/100th of 1% of its current age. Evidence of the Big Bang was written all across the sky, in the glow of what is now called the cosmic background radiation. Satellites have since mapped the cosmic background radiation in detail, revealing how matter and energy were distributed in the infant universe. In this map, created by the Planck satellite in 2013, the slightly more massive regions are colored blue. Over billions of years, they went on to form clusters of galaxies. The less massive regions, colored red, became cosmic voids. Because it takes time for the light from distant objects to reach Earth, everything we see in the sky belongs to the past. These spheres mark distances from Earth in light years. When we observe galaxies billions of light years from Earth, we see them as they looked billions of years ago. We're flying through a 3-dimensional atlas of millions of galaxies. The gaps are regions we have yet to map. Beyond every galaxy we could ever observe, farthest away in space and furthest back in time, the cosmic background radiation marks the visible edge of our observable universe. evidence of what happened even earlier in cosmic history can be found right in our own neighborhood. In 1995, NASA's Galileo spacecraft released a probe to study the upper atmosphere of Jupiter. Scientists had calculated that the simplest atoms were forged during the first minutes of the Big Bang. One of them, heavy hydrogen, is destroyed inside stars, so it should have become ever rarer as the universe evolved. Unlike Earth, Jupiter acts as a cold storage locker, preserving samples of the materials from which the solar system formed more than 4 billion years ago. By analyzing the giant planet's atmosphere, scientists could check how much heavy hydrogen existed back then. Observations of the cosmic background radiation had established that the universe was once hotter than the surface of the sun. Galileo's audacious exploration of Jupiter found enough heavy hydrogen to confirm that during the first minutes of the Big Bang, the entire universe was hotter than the center of the sun. Hot enough to forge simple atoms. But while scientists were piecing together the history of atoms, evidence emerged that most of the matter in the universe isn't made of atoms at all. The universe contains clusters of galaxies, like this one. Each cluster, home to trillions of stars, generates enough gravity to warp the space around it into a giant lens that distorts our view of the galaxies beyond. But when we calculate the strength of these gravitational lenses, we find that each cluster must contain 6 times more matter than we can see there. So now it seems that all the glowing stars are just the glittering froth on a dark cosmic ocean of invisible stuff called dark matter. The motions of galaxies within each cluster confirm the presence of dark matter. The galaxies orbit too fast to be held together by the gravity of normal matter alone. Remove the dark matter, its lensing stops, and the cluster flies apart. Scientists find that dark matter, shown here in black, was essential to forming the large-scale structure of today's universe. This computer simulation traces how cosmic structure evolved over time. The bright knots contain thousands of galaxies, drawn together by the vast sheets and tendrils of dark matter. These knots grew from the densest regions seen in the cosmic background radiation. The less dense regions of the background became cosmic voids, big, empty bubbles, hundreds of millions of light years wide. The gravity generated by normal matter is much too weak to create this cosmic web. Dark matter must be doing the job. What is dark matter?